So hi, everyone. Thanks for joining us. By the way, I'm Caroline. I'm just replacing Ingo for today since he wasn't available. So today's speaker is Alexey Vlasenko. So Alexey got his PhD from the University of California in San Diego and is now a postdoc at North Carolina State University. And he will talk about multi-angle simulations of matter-neutrino resonance. So just before we start, I should remind to please put off your microphones during the talk. And if you have questions, please wait until the end unless it's very urgent. So that's it. So Alexey, whenever you are ready, please.
Okay, thank you, Caroline. So I will be talking about matter-neutrino resonance, which is a type of flavor transformation that can be seen in compact object mergers, potentially. In hot, dense environments, such as the early universe, or in compact object mergers or in supernova, the neutrinos can play a very important role. They have a long mean-free path. They can pass through matter, carry energy, momentum, and lepton number around. And the electron neutrinos interact with matter differently than other flavors because there's a lot of electrons around and not a lot of muons. So neutrino flavor transformation matters. We actually need to know what flavor state the neutrinos have at each point in order to make predictions of the effects that the neutrinos will have. So flavor physics can affect things that we can actually observe. For example, elemental abundances from our process nucleosynthesis. We can get observable spectra from supernova, possibly if we're lucky enough to get a nearby merger, but also the neutrino spectra contribute to an effective in the early universe, so we can actually do some neutrino measurements there. And of course, the neutrino flavor can affect the dynamics of mergers in supernova because the electron neutrinos transport the energy and momentum differently in the system than do the other flavors. So one way to describe neutrino flavor is to introduce a flavor density matrix. And there is a choice of basis where the diagonal elements just give you the occupation numbers for the three flavors of neutrinos, and the off-diagonal elements tell you the coherence information between the flavors that allows for things like oscillations. So for each neutrino momentum bin, we'll have two matrices, one for antineutrinos, one for neutrinos, and those matrices evolve according to a familiar Schrödinger equation. And the Hamiltonian in the Schrödinger equation has three parts. There is a neutrino potential, which is a self-interaction between neutrinos and other neutrinos. There is a matter potential, which comes from interaction of neutrinos with each other. And then there is a vacuum term, which is basically the square of a mass matrix. And that's what mixes with flavors and can cause oscillations. We find that neutrino flavor transformation can occur when some combination of scales in the Hamiltonian is comparable to a vacuum term. So for example, when the matter potential is comparable to a vacuum term, we can get a level crossing where the effectively heavier neutrino and the effectively lighter neutrino in matter change places. And that's known as the MA2 effect, and that can lead to very efficient flavor transformation. Then the neutrino potential is comparable to a vacuum term. We get another phenomenon called collective oscillations, which can transform neutrino flavor even when matter potential is very high. And finally, when the sum of the matter and the neutrino potential is comparable to a vacuum term, we have something called the matter-neutrino resonance. And the matter-neutrino resonance is very interesting because the matter potential and the neutrino potential can be very large individually. So this can take place at very high densities and high neutrino fluxes. But if there is a cancellation between the two, we can still get flavor transformation. And this cancellation can potentially happen at high densities, so the neutrinos still have a purchase on the proton to neutron ratio, for example. While for the MA2 effect and the collective oscillations, it tends to happen at much lower density when the neutrinos have already decoupled, or rather the matter has decoupled from the neutrinos. So in a compact object merger, there's occasionally a situation where the antineutrino flux is larger than the neutrino flux. So basically, we're taking neutron-rich matter, we're heating it up, we're converting some of those neutrons into protons, and as a result, we emit some electron antineutrinos. So if this happens, the neutrino potential will have the opposite sign to the matter potential. And in that case, we can get exactly this type of cancellation that I was talking about, called the matter-neutrino resonance, or MNR. And as I mentioned, this can lead to flavor transformation even at very high densities, when the matter and the neutrino potentials are individually much larger than the vacuum term. So some previous work on this have been done in what's known as the single angle approximation. So in the single angle approximation, we assume that the neutrino flavor evolves the same way for all neutrino trajectories. And we just select some average neutrino trajectory and we follow the flavor evolution along that. And we assume that all the other neutrinos are doing the same thing. In a typical model, one would have the matter potential be proportional to the radius to the -3 power, and the neutrino potential drops off faster as r to the -4. It's because there's 2 powers from the flux being diluted and 2 powers from the angular dependence of the cross section. And for the neutrino potential initially larger than minus the matter potential at some small radius, there is a cancellation at some value called the MNR radius, where the neutrino potential is minus the matter potential. In the single angle case, this leads to a very unique pattern of flavor transformation where the neutrinos transform fully. So the survival probability goes to from 1 to 0, which means that all the electron neutrinos have been converted away to other flavors. While the antineutrinos transform a little bit at first, but then they return to the original state. And this pattern of flavor transformation, the way it operates is there is a feedback mechanism that keeps the total potential near 0 until the transformation is complete. So basically, on the previous slide, the neutrinos transforming will enhance the magnitude of the neutrino potential. So it tracks the matter potential and maintains this resonance for a very long time, hundreds of kilometers. Now, that was a single angle simulation, but realistically, the neutrino potential strongly depends on the propagation angle. So there is no reason to think that different neutrinos in different trajectories will transform in the same way. So the Hamiltonian, the neutrino potential has basically 2 components. It's in spherical symmetry, it's a 4-vector. So there is a time-like component and a radial component. And the neutrino potential is the time-like component minus the radial components times the cosine of a propagation angle. And the 2 components become similar for a large radius. So in this illustration here, the neutrino that is following the trajectory at angle θ1 has a smaller neutrino potential than one following the trajectory of θ2. So the location at which the cancellation happens and the MNR takes place depends on the value of the neutrino potential. So this is a crucial point. Neutrinos in different trajectories cross the MNR at completely different locations. In the single angle model, they cross all at the same point. Because the MNR is spread out over a large region, multi-angle models with MNR can be expected to behave differently than single angle ones. And so the conclusions we can draw from single angle simulations are limited. And there have been some recent examples of multi-angle models. So for example, there is a paper by Shashank Shalgar that looked at a beam with some opening angle. And here we're doing a spherically symmetric model. And eventually we want to do a cylindrical source to be able to simulate something like emission from an accretion disk, but that's a very computationally expensive problem. So for now, I will be talking about the spherical bulb model. So the spherical bulb model is the simplest self-consistent multi-angle model. We basically use just two flavors for simplicity. We also make the single energy approximation. So we just take an average neutrino energy rather than follow the different energies differently. And this works pretty well for matter-neutrino resonance because we find that neutrinos at different energies do in fact transform in a similar way with MNR. And this model captures the key feature of multi-angle systems, that the location of the MNR depends on the trajectory. So this is a sketch of a geometry that we're using. The neutrinos are emitted from a surface known as the neutrinosphere. They are labeled by the initial emission angle theta 0, and then we use a cosine of that as our label on the neutrino trajectories. This U0, which is cosine theta 0, will turn into a different angle, a different value U at some radius. And we're also assuming that the matter potential goes as r to a minus 3 and the neutrino potential goes as r to a minus 4. But it has this dependence on the propagation angle. So it's basically the neutrino number minus the antineutrino number minus u times the neutrino flux minus the antineutrino flux. The model has some parameters. So we choose a neutrinosphere radius, which also sets the flux. The bigger the neutrinosphere, the higher the flux. We choose the MNR radius, and that's different for the different bins. So we just define it at which the radially emitted neutrinos have the MNR. And this parameter called alpha, which is a ratio of antineutrino contribution to the potential to the neutrino contribution. So to get an MNR, we need antineutrinos contributing more, so we need alpha greater than 1. We also choose a vacuum mixing angle. We use theta 1,3 here. Mass hierarchy, we tested both normal and inverted, and the results are very similar. So the results I'll present will be normal. So for a benchmark model, to show that all this works, we choose a neutrinosphere of 15 kilometers, MNR radius of 60 kilometers, alpha of 1.4, and the normal hierarchy with using the mixing angle theta 1,3. So there are some numerical issues that we had to solve. So first of all, the calculation converges poorly with number of angular bins, and we need something like 4,000 trajectories to get convergence. There are some problems with stiffness at parts of the flavor evolution. And so we have to occasionally use a computationally expensive implicit integrator to skip over the stiff points. And we test for convergence by repeating each run with worse angular resolution and worse error tolerance. And if the results remain the same, we conclude that it's converged. So this slide shows the survival probabilities in our multi-angle model in contrast to the single angle one. And we see that there are some shared features. So the neutrinos transform more than the antineutrinos, just like in the single angle case. But while in the single angle case, neutrinos transform almost completely while the antineutrinos return to the original state, in the multi-angle case, it's an incomplete transition. So antineutrinos do not return all the way to the initial state, and neutrinos do not transform all the way. And also, if you look at the scale on the bottom, in the single angle case, the transition takes hundreds of kilometers, while in the multi-angle case, it's a lot shorter. It takes place over maybe 100 kilometers. So this is the neutrino potential. You saw a slide before from single angle where there is a feedback mechanism that keeps it at 0. Actually, this is a total potential, neutrino plus matter. So when it's at 0, we're in the resonance. In the multi-angle case, there is a bunch of trajectories. So the top line shows the potential for the radially emitted bin, and the bottom line shows the potential for the tangentially emitted bin. And there is also 4,000 other bins in between, which have intermediate values of the potential. So we see that actually at first, the potential becomes more steep. And then it flattens out and forms kind of a similar type of plateau as what we see in a single angle case, but that happens near the end of a transition when the tangential bends reach resonance. And instead of taking several hundred kilometers, this flat region is only about less than 100 kilometers long. This slide shows the survival probabilities as a function of the emission angle. The left-hand slide is at 120 kilometers, about halfway through the transition. So we see that some bins have gone through resonance, while the ones on the left haven't yet. And then the right-hand slide is after the MNR is complete, and the survival probabilities have approached their final form. So the key points here is that the radially emitted bin so V0 is cosine squared of the emission angle. So at cosine of the emission angle of 1, that's the radially emitted neutrinos, the survival probabilities aren't that different between neutrinos and antineutrinos, but for the tangentially emitted neutrinos on the left-hand side, the survival probabilities separate, much like in a single angle case. So yes, as I said, the radially emitted neutrinos neutrinos and antineutrinos evolve together, but for the tangentially emitted ones, there's a large difference in the survival probabilities. And this happens because near the end of a transition, the tangential neutrinos are the only ones that are near resonance, so they're the only ones that are transforming. So effectively, we get something like a single angle situation where only a narrow range of angles of the neutrinos are transforming, so we get single angle-like behavior. Those neutrinos are small in number, but they have the greatest leverage in the Hamiltonian because it depends on the trajectory angle. And so they can actually sustain a matter-neutrino resonance for a limited time. And that explains why the Hamiltonian flattens out and why those survival probabilities on the left-hand side separate for low V0. So we did a simple model of matter composition where we just have neutrons and protons in equilibrium with the neutrinos, and we neglect electron capture. This is somewhat justified in the region where the MNR takes place. In fact, the neutrinos do dominate the matter composition in that regime. We find that the MNR results in a modest YE decrease by a few percent. So it's not a huge effect, unlike the single angle in the single angle calculation, but it does make the matter slightly more neutron rich. And at YE of 0.4, 0.5, small changes like this can have a big impact on the outcome of nucleosynthesis. So next, we test the sensitivity of our model to the parameters. So first, we vary the antineutrino to neutrino ratio, alpha. So we find that as we increase alpha, there is a little bit less flavor evolution overall, but there is more separation between neutrinos and antineutrinos. So the reason why there is less flavor evolution is because as we increase alpha, the neutrino potential goes up. So, and to keep the MNR radius the same, we also increase the matter potential. So all the potentials are large compared to a vacuum term, and essentially the effective mixing angle goes down, so that all the transitions are less adiabatic. And the reason why there is more separation for high values of alpha is because basically there is flavor transformation has more leverage on the potential in this way. The neutrino potential can basically change by more if there is a lot of difference between neutrinos and antineutrinos. So next, we look at the sensitivity to the neutrino sphere radius, which also determines the neutrino flux, as well as the angles at which the trajectories cross. So we keep alpha at 1.4 and MNR radius at 60 kilometers, but we vary the neutrino sphere. So on the left, we have a very compact source, 10 kilometers. We get more flavor transformation. In the middle is our benchmark model. On the right, we have bigger neutrino sphere and a higher flux, so we get a little bit less flavor transformation. And again, this is because as we go to the right, the fluxes and the densities are all higher. And so basically the transition is less adiabatic. Nevertheless, even at a large neutrino sphere radius, we see a lot of flavor evolution. And finally, we change the MNR radius. So if we bring the MNR closer in, the transition takes place at higher densities again. There is less flavor transformation. If we bring the MNR radius further out, we get more flavor transformation. So next, we tested a different matter density profile. So before, in the slides before, we had the matter density be proportional to r to the minus 3 power, and now we're doing 1 over r matter potential instead. So we find that a shallow matter density profile does effectively suppress the transition. So in the slide on the left, there is almost no flavor transformation. However, if we increase the MNR radius, we can restore the flavor transformation. So if we make the MNR radius 100 kilometers instead of 60, we see a very similar pattern as we did before, despite a completely different matter profile. And then finally, we want to address this issue that is present in particular in compact object mergers, but also in supernovae, and that's that a significant fraction of neutrinos do not actually come from the neutrino sphere. So for example, in the merger, we have disk that contributes, an emission from the disk can contribute about half the neutrinos. There is also some neutrino scattering off of matter outside the neutrino sphere, and while those scattered neutrinos are relatively few in number, they travel at very large angles, so they have a very large impact on the neutrino potential. And so we make a relatively simple model that can account for this. So instead of starting the simulation at the neutrino sphere, we started at an extended radius, which it's below the radius at which flavor transformation begins, but it's higher than the neutrino sphere. And then we just add some neutrinos on shallower trajectories. So if we start at the extended radius with the neutrino bulb model, that's the red line in this plot, we just get this kind of step function where almost all neutrinos are traveling almost vertically because we're far away from the neutrino sphere, and there are no neutrinos on shallower trajectories. But instead, we can use the blue line where we add a bunch of neutrinos on shallower trajectories and see what that does. So this is the result of a simulation. So we move the MNR radius out a little bit to 90 kilometers, and that's because of using the extended neutrino sphere, the neutrino potential is enhanced by something like a factor of 10, because all those neutrinos on shallow trajectories contribute a lot to the potential. So we basically use that weight function from the previous slide, and we find that the pattern of flavor transformation is very similar to the bulb model, except that the MNR takes a little bit longer, until about 400 kilometers, rather than about 200 in the previous case. And this is just because the long tail of a neutrino distribution takes a very long time to pass through the resonance. So, but nevertheless, the behavior is very similar. So we don't expect, for example, effects from neutrino emission from the disk to ruin this in any way. So in conclusion, we did multi-angle calculations of matter-neutrino resonance, and we found that there's a new type of flavor transformation that occurs in the presence of MNR. It's qualitatively different from what we see in the single angle case, and but it has some similar features. So for example, the neutrinos and antineutrinos transform differently, with neutrinos transforming more. And because the neutrinos and antineutrinos transform differently, this alters the proton to neutron ratio, which in turn can have effects on nucleosynthesis. So the results are very robust. We tried a wide variety of different conditions. We always see sort of the same pattern of flavor transformation. And so we conclude that neutrino flavor transformation due to MNR is likely to be important in compact object mergers, although it looks a little bit different than what single angle simulations suggest.
Okay, thank you. Let's clap for Alexei. So any questions?
It took us a while to unmute.
You can also use the chat if you want.
I have one question. Can you hear me?
Yes.
Can you tell me a little bit more about the impact on nucleosynthesis? So it changes the neutron to proton ratio. So does that change? Do you expect in a merger that would change the abundances or also the amount of mass ejected or both?
Well, let's see. So yes, it would change both. So we're talking about the region kind of close in that's heavily impacted by the neutrino fluxes, right? So, and we find that MNR will bring down the YE a little bit. So it makes the matter slightly more neutron rich. So what this can do is, so it basically makes our process easier.
Oh, I see. Okay.
Yeah.
But I'm a bit confused. If I imagine the merger, so there is this dynamical ejector and the jets, and there's a disk and the neutron star forming in the middle. And so where are the neutrinos and
So this is,
which of the outflows are affected by this?
yeah, with disk outflow, this would affect the disk outflow, the dynamical ejecta. If they never come close to the center, then the neutrinos don't do very much there. But in the disk, for example, the composition can be affected by the neutrinos.
And the neutrinos come from the center, or?
They come from both the center and the disk. So basically the point of the extended neutrino sphere model is we can't really do a disk in a spherically symmetric model, but essentially the extended neutrino sphere is like a spherical analog of a disk. So the neutrinos
sounds interesting.
Yeah, so the neutrinos are coming from both a proton neutron star and the disk, except we made the disk spherical because we are doing spherical symmetry for now.
Yeah, so I could just add to that it will have a very major impact on any kind of wind type nucleosynthesis that comes off the hypermassive neutron star or the accretion disk. And it has a smaller influence on the collisional ejecta, but probably very little on the tidal ejecta.
Yeah, so anything that's evaporating off the disk, for example, can be strongly affected by neutrinos.
And that's not included in current simulations?
No. Neutrino flavor physics are not included.
So you're going to include it then, or what's the next step?
Yeah, so in the future, we would like to find some way to include the neutrino flavor transformation in merger simulations. Now, it may be difficult to do because the kind of angular resolution we need here is very high. But if we know how MNR works, we can identify criteria for predicting just where it will occur based on physical conditions. So then maybe we can basically be able to predict the outcome of MNR and put that into the simulations. So that's one idea.
More questions? So I'm just curious to know, and typically how costly are these calculations? Like how long do they take, for instance?
The single energy ones can be done on a laptop in a few hours, so okay. They're not costly. Some of the ones with the extended neutrino sphere do take a little bit longer, but it's still something that can be run on a personal computer in a few days.
Okay. I see. Okay, so if there are no further questions, thank you again, Alexei, and thank you all for joining, and we'll see you next time. Bye.
Bye.
Thank you.
Thank you.